My name is Mario. The work I'm presenting today is actually joint work with John, Zach, our advisor Fabián, as well as Dave, Bala, and Walter. And today, I'm going to talk to you about a measurement experimentation platform that's hosted by end users located at the edge of the network. The internet is growing at a very fast rate, with over 1/3 of the world's population already using it. This growth has been driven in part by the increase in broadband technology and affordability, which has made the internet not become only larger, but also more spread out and diverse. Although many of our distributed systems are actually located and run at the edge of the network, and it is well known that when we measure them from the core, they actually look different, the truth is that we lack measurement platforms suited for experimentation at the right scale, with vantage points in the right location, and that provide sufficient control for us to be able to launch these experiments. And while we do have platforms like Planet Lab that actually provide great fine-grained control, the fact is that it doesn't scale really well, and their vantage points are located in research and academic networks. Other platforms like Dimes do provide the potential for scale and the actual view that we want, given that they run at the edge of the network, but it actually provides little flexibility in terms of control and experimentation. What we do need is a platform that combines the best of both worlds. A platform that provides flexibility for experimentation at scale, and that it's run by end users located at the edge of the network. But for such a platform to be useful, it not only needs to be running at the end user's machine and for it to be scalable, it also needs to be able to guarantee the safety of the volunteer nodes. It needs to be able to control the impact that experiments will have on the underlying network and on the actual resources of those machines. And it needs to find a fundamental way of being able to share the resources between multiple experiments and multiple experimenters. Today, I'm presenting to you Dasu, which is a prototype of such a platform. Dasu is a software-based measurement experimentation platform that's hosted by end users located at the edge of the network and relies on direct incentive using broadband characterization for users to download it. Dasu, from its inception, was designed with two purposes in mind. On the one hand, Dasu allows end users to characterize the service they receive from their broadband networks. On the other hand, it provides experimenters with support for experimentation from the edge. Using these two purposes by design in Dasu actually aligns the objectives of both end users and experimenters, at least in 4 very important ways. First, both end users and experimenters can actually benefit from having large coverage in order to be able to capture network and service diversity. They both benefit from having large availability in order to be able to catch changes in policies and on schedule events. They also benefit from being at the edge, being that this is the view that we're trying to capture. And finally, they both benefit from being extensible. In the case of end users, in order to be able to remain effective in the face of changes in the ISP policies, and in the case of experimenters, in order to be able to extend the platform with new measurement probes. But although participatory platforms that include end users do provide many of the benefits that we're looking for, the truth is that they also face us with a lot of challenges that we need to solve. One of them is the lack of dedicated resources, which means that as experimenters, we cannot just run any experiment we want on these machines. For instance, some experiments that might include related to censorship might be out of the question because this might get end users in trouble. So safety for volunteer nodes is key. Another problem that brought about by these platforms is actually brought about by the large scale that we're looking for, and it's the fact that a larger number of vantage points will more likely can have a very negative impact on specific destinations on the internet. And finally, it's actually related to the lack of control in the availability of nodes. It's the fact that we can run whenever we want the experiments, since we don't control when the users are there. And we can even guarantee that the users will actually be available at a location that I'm interested in measuring from. So today, I'm going to present to you the design and implementation of Dasu and how it addresses some of the challenges that I just discussed. I mentioned that our current prototype is called Dasu, which is a Japanese word that signifies to reveal or to show. Our current implementation is actually installed as an extension to a popular BitTorrent client. And because it relies on this P2P implementation, it receives a lot of benefits from it. But most importantly, it gets a large set of vantage points that not only growth with the internet, but growth where the internet is growing faster, which is at the edge. Right now, Dasu, as I said, relies on a host application, which is BitTorrent, but it could be hosted by any long-running application or even as a standalone client, which we're currently working and should be released in the next month or two. Dasu currently has been installed over 90,000 times from over 151 different countries. And this has been achieved with minimal advertisement in the past couple of years. But Dasu wasn't only designed to be a platform that is hosted at the edge, it was also designed to be a programmable and easily extensible platform that reduces the efforts needed to develop and deploy large-scale measurements from our vantage points. So let me give you a quick look at the architecture of the system, and with a simple example that shows the lifetime of an experiment. The two main components of our system is the Dasu client and the infrastructure servers that support it. When Dasu client comes online, it contacts the configuration service and receives information from the configuration service about the number of probes, the frequency of probes, and the location where the results should be submitted once experiments are completed. Then the clients contact the experiment administration service that actually assigns experiments to clients based on their characteristics, such as their IP address, their prefix, or the AS they belong to. Then, periodically, Dasu clients contact a coordination service and submitting updated information about the completed probes, which responds with what we call as an experiment list, which limits the number of probes that clients can send based on the overall and aggregate traffic utilization of the system. Finally, when the experiment is complete, Dasu clients contact the data service and report the results. For Dasu, we opted for a rule-based declarative model for experiment specification. Here's an example of the syntax that we use by our experiments. Our experiments are basically expressed as a combination of rules, which are expressed using a small subset of the Java language. For the most part, many of these constructs are similar to the Java counterpart. For instance, package name, imports, and some variables. But the two key components of these experiments are the functions and rules. The functions are basically ways for us to put semantic code in the experiment and are actually used to extend the rules. Rules are simple when-then constructs that specify a set of actions to be executed whenever a set of conditions are met. For instance, the drive of the system are the rules, which are normally fired in the case the client wants to request launching a probe module and even to get the results from the experiments back and report them. Each Dasu client runs these experiments inside a rule engine, which parses the rules and fires them as required. These rules or these experiments actually are allowed to request experiments from those available in the base clients, which right now include a set of probe modules, which include, for example, trace routes, pings, and NDT, for instance. But the scheduling of the probes is actually made available through the coordinator, which actually is also in charge of making sure that the resource utilization in the system doesn't go too high. Finally, when experiments are done, they are simply reported through the measurement service, through the reporting service, I'm sorry. So now I want to show you how Dasu addresses some of the challenges that I discussed previously. The first one being the lack of dedicated resources. The fact is that we can run any experiments in these nodes. So Dasu implements several mechanisms to minimize resource consumption in those machines and protecting volunteer nodes. In order to protect volunteer nodes, every experiment in Dasu runs inside its own rule engine, which is run inside a sandbox environment, which is represented by a separate external JVM that actually runs with restricted resources and actually implements restrictive security policies which are similar to those applied to on-site Java applets. Also, Dasu clients run a resource profiler, which continually monitors the resources consumed by the system, and also have a watchdog timer, which we use as a last resort measurement security measure that triggers a client shutdown if anything goes not according to plan. For instance, when CPU usage goes above specific threshold for too long. Also, all communications with the infrastructure servers are done using secure channels, including HTTPS, and every experiment that we run is digitally signed. To limit resource consumption on the system, and to minimize the impact on the user's performance, Dasu implements predefined limits on the number of probes that can be sent per type, as well as the aggregate bandwidth that they consume. And probes are only scheduled to be launched when there's a low utilization period in the system. But despite these probe limits, the fact remains that a large number of Dasu clients working at the same time towards the same destination have the potential of overloading it. To limit this risk, we introduced two new constructs, which we called experiment leases and elastic budgets. Every Dasu client periodically reports to a coordination service and reports information about the probes that it actually has completed so far. The coordination service uses this information to compute aggregate load on a per destination basis, using every report sent by every client participating in an experiment, and generates what we call the experiment lease to be distributed to these clients. This lease actually limits the number of probes that these clients can send on a per destination basis, using the aggregate load of every client in the system. But because of churning the system on those end nodes that we can control, the number of probes that they will actually be able to send before the lease expires is going to vary wildly. So we might be underusing the system resources at some point. So to limit this impact, Dasu introduces the concept of elastic budgets, which basically gives each client some leeway in terms of how flexible the limits imposed by the system are. So now let's take a look at the dynamics of the system and how the dynamics of these end nodes, which we can really control, affect our experiments. The maximum length of an experiment that we can run using any Dasu client actually depends, in part at least, on the client's session times. By session times, I mean the elapsed time between the time the clients come online and leave the network. So an important first question would be whether the session times of Dasu clients is sufficiently long to allow for meaningful experimentation. We find that in this case, the median session times of Dasu clients is approximately 3 hours. To put this into perspective, we compare them with the experiments run on different slices in Planet Lab, and we found that 50% of the Planet Lab slices don't run experiments that are larger than 3 hours. Another important question is what number of peers are actually available in the system at every point. We try to capture this availability by using the percentage of peers online at any given hour over a 7-day period using Dasu clients. The figure shows the hourly fraction of available peers broken down by the hour of day. We find that the percentage of available peers varies between 39 and 43% of the number of unique peers seen throughout the day. And if we look at the number of ASs that we see throughout the day, it varies between 52 and 63%, which hints at the stability of the number of Dasu clients that we see throughout the day. Now, let's look at how the load on these clients affect our experiments. The figure shows the CDF of the fraction of probes delayed by each client. Remember that each Dasu client limits when the probes are launched based on the underlying host utilization of resources. In this case, we're looking at the utilization of 80% on the upload rate and download rate of the client. And we see that if we look at the download rates for 85% of the peers, the scheduled probes can be launched right away. Dasu capabilities actually has allowed us to launch very different types of experiments because of its capabilities and because of the location where the vantage points are. But today, I want to share with you one specific case that illustrates the unique perspective that we get from Dasu. And this is using the evaluation of a recently proposed DNS extension, which is called EDNS. Well, the problem basically that EDNS is trying to solve is the fact that CDNs typically map clients to a replica server based on the location of the DNS server that contacts them. The growing uses of remote DNS servers then makes it a problem for CDNs because clients are normally being redirected to servers that are far away from them. The idea of EDNS is then to avoid this problem altogether by changing the localization approach and getting the DNS servers that contact them to forward the information about the location of the clients. For instance, in the form of the prefix where they belong to. But the question we're trying to answer with this study is EDNS really effective? In order to be able to evaluate whether it's actually effective, we would need to use a platform that is located at large scale at the edge of the network, where with vantage points throughout the world, that allows us to launch interrelated measurements between them in a flexible way. For this experiment, we used over 1,000 Dasu clients located throughout the 4-month period. And we measured the benefits of the extension using HTTP latency to the first byte of content. Keep in mind that we need to first probe the DNS servers using EDNS and without EDNS, get the replica servers and being mapped to, and then measure latency using HTTP. While in the graph, we break down the users by the location or continent where they are. While we do see that most users do benefit with this extension, we see that North American clients generally obtain higher percentage savings when compared to those in Europe. But interestingly, when we look at clients located in Oceania, we see that they typically see really low, bad latencies when they do not have EDNS. And they do gain 70 to 90% performance when they actually have it enabled. Based on this information, on this observation, actually, the firstborn of Dasu was the first child of Dasu was born, which we call name help. Actually, name help is an end-user-based approach that actually tries to get the advantages of EDNS without the need for it to be deployed. In about 5 months, name help has been installed over 52,000 times. So I guess this is the common case where the children is being more successful than the parent. In summary, today I presented to you Dasu, which is a measurement experimentation platform located at the edge of the network, which relies on direct incentive as a model for adoption for end users. I showed how the participants collectively offer a broad network coverage, high availability, and enough fine-grained control to deploy meaningful experiments. If you're interested in actually using Dasu for your own experiments, please just contact us. Thanks. Now I will take some questions. Sorry, before I get in trouble with one of my co-authors, Bala made me post this here about an upcoming conference. So. But now I will take some questions.
Indy Gupta, University of Illinois. I have two sort of related questions. One is, what kind of debugging support do you provide in Dasu? Because in Planet Lab, debugging is horrendously difficult. The second question is, how do you terminate runaway experiments?
Right. For your first question, right now, the way we allow experiments to be uploaded to the clients is through us using the Apple Store model, where we have to vet the content of experiments. And the actual clients do look at the abstract syntax tree of the experiments in order to limit what they can actually import, for instance. In the case of runaway experiments, we do have the resource profiler that actually looks at the CPU usage if anything went awry with our vetting of the experiment. And it sees that the CPU usage, for instance, went over a specific limit, then it will immediately shut it down.
So if I launch an experiment and I want to kill it right now, is that still possible? I launch an experiment, a measurement experiment, it's running on, say, 30,000 clients.
Right. Absolutely, you can shut it down, but you can shut down the deploy of more experiments on different nodes. If it's already running on it, it will until it ends, we have no real control over it.
How long does it take? How long does the termination take?
It actually depends, really much depends on what we're doing, but we've seen that in our experiments at least, they've been able to complete, most of the experiments completed in about 5 minutes.
Okay, thank you.
Sure.
Sorry, I thought of my question late. Mike Whitty, Montana State University. Do you have any plans on extending this to mobile devices?
Actually, I think so. There's a different student in my lab that focuses on wireless, and I think he's working on something related. I can't really say for sure, but we can talk online. My advisor is here, so we can talk about it.
Thank you.
Sure. Thank you.